All right, this is lesson 7.2. We're going to talk about slope fields and Euler's method. Yes, it's pronounced Euler, not Euler, kind of like the Edmonton Oilers hockey team. We're going to relate this to what we did in lesson 7.1 because a slope field is really just a graphical representation of all the different sets of slopes that you get from a differential equation. So remember that we looked at differential equations in lesson 7.1? They all involved a derivative, and that derivative represents the slope for a function. So once again, in lesson 7.1, we learned how to solve differential equations by separating the variables. And even if you cannot separate the variables and integrate, you can still use a differential equation to plot the slope for a function. So let's take a look at example number 1, and I'd like you to just quickly calculate the slopes by the given differential equation. And this is the equation dy dx equals to negative x over y at the following points. So in essence, all you need to do is just plug in the numbers. So we got x equals to 3 and y equals to 2. Yep, negative 3 halves for part A. For part B, we'll plug in negative 1 and 3 for x and y. And I hope that you can see the slope is 1/3. And then for part C, yes, that's negative 2 divided by negative 1, that's negative 2. And finally, part D, I hope you got the answer of 1. Now, I have another question for you. It says, why can't you find slopes when y equals to 0? So what is the big deal when y equals to 0? Yeah, y equals to 0. Who cares? You care, I care, we all care. Because, yes, you can't really divide by 0 because the slopes are undefined. And divide by 0. Good. Okay. So taking a look at the next question, number 2 here says, okay, I want you to now find and plot the slopes given by dy dx that equals to negative x over y. Hey, it's the same equation from example number 1 for each of the remaining marked points or the dots in the coordinate plane at the right. So if you see this little coordinate plane, you see these little dashes, the dashes actually represent the slopes at that particular point. Okay. Now, as a quick review, if I had the slope value being equal to 0, you would draw a nice horizontal line showing that the slope is 0. If I had something like this, the slope is 1, I hope you can remember that you'll be drawing a nice 45-degree line going upwards. That's m equals 1. And if I had something that's negative, yeah, hopefully you remember going downward, the 45-degree line going downward. Now, as m gets larger and steeper, hopefully you'll see that it gets like that. And then if I do the same thing going negative, it'd be steeper negative. So really what you need to do is calculate the slope and then draw a little dashed line to represent the actual slope. Okay? So I'd like you to try to do that for every single missing point, or every single point that has a missing dashed line. So here. Okay? And then when you're done, come back and double check to see your dashes match mine. All right? So press pause right now and go ahead and try yourself. Oh, I know these are all 0, right? Because x is 0. These all seem to be -1. And then as I get closer, they get flatter, like that. I know this one here is +1. This is +1, also +1. And as I get closer and closer, they get steeper and steeper. Hopefully you know that there's nothing that's happening here when y equals 0, so there's no slope, or I should say undefined, right? Because I can't divide by 0. And then everybody else, how about something like this, that. And once again back to 0. So if you drew all these dashes and you got something that looks like this, bravo, you are on track with me. Okay. Now, in example 3, it says, look at what you did in example number 2. What you created is something that is called a slope field. Yeah, that whole thing here is a slope field. Now, starting at a particular point, let's say I asked you to start at 0, 1. Follow the flow of the slopes to actually sketch the solution curve containing 0, 1. So remember how in lesson 7 we had to solve for y, and then we plugged in a number to like solve for c to actually get the particular solution? That's what I want you to do right now, but I want you to do it graphically. So starting at 0, 1, let's have you right over here, 0, 1. I want you to do what? Well, sketch the solution curve. So it says your graph should be parallel to the slope lines and be like the average of slopes whenever it goes between the lines. So if I were to go a little bit to the right, can you see how the slope kind of goes now downwards? It's a negative slope. So as I approach that point, I should also be going downwards, and it should be parallel to what I had before. And if you kind of see, it gets even steeper over here. So I'm assuming that the graph looks something like this. Okay. Now maybe I drew it a little bit not so nice, but yeah, something like that. Okay. And similarly going to the side, same thing, right? I see that, oh, it has to be parallel here, and it kind of curves down. Okay. Notice I better not actually put an open dot. Oh, sorry, I should put an open dot at the x-axis because there is no slope there. Okay. That makes sense because I said here the solution curve must represent a function whose domain is the largest possible open interval containing the given point. So you see I continued to the left and the right until I hit the x-axis because that's where I had an issue with the domain, right? There's nothing that's defined there, so I better stop, okay? Do not continue down here, and that would be a mistake. Now, do another solution curve for me, please. Okay, try this one here. That goes through negative 1, 1. So negative 1, 1, I think is this one here. So it's going upward probably like this, and then here it flattens out. And then I guess it comes back down like this somehow. So yes, I get like another graph very similar to the one in blue, just a little bit larger. And then last but not least, I said 0, negative 3. So let's do one here, and I hope you can see that I get a curve that looks like this. And once again, open dots as I get to the x-axis. Now, what type of graph does this differential equation seem to be producing? I hope you can say that this is a semicircle. So notice your particular solution to this differential equation, dy dx equals negative x over y, is some sort of semicircle. Right? Now, just a quick note, the most common error that students make in sketching a particular solution to a differential equation is to actually extend the graph too far and create a graph that is not a function. So once again, if I took the black one and I kept going like this, ooh, sorry, that's not a function anymore. That's a problem. Okay? And also, you crossed a place where the slope is undefined. That's also a problem. Okay? So once again, why is the x-axis a boundary for the differential equation then? Yeah, once again, it's because the derivative is undefined when y equals to 0. So at this point, we really can't determine if the solution is a vertical or discontinuous. So really, it can't be extended past the x-axis. We just don't know. All right? Now, we've done the visual picture, and now what I'd like to do is review what we did last lesson. Can you now go and solve this differential equation? Okay? And then find the particular solution for it that passes through the point 0, 1. That would be the one in blue. And also then 0, negative 3. That would be the graph in black. And let's see if we can get the equation of a semicircle. All right, so what did we do last day? Separate variables. So we wrote down dy dx equals negative x over y. And we want to separate them, so bring all the y's to one side, making sure that dy is in the numerator position, and then bring all the x's to the side with the dx in the numerator position. Y dy, negative x dx. Beautiful, you've separated the variables. Now it's time to anti-differentiate both sides. So the antiderivative of y is just y squared over 2. And then the similar thing, negative x squared over 2. And don't forget, plus c. And I want to solve for y, so I'm going to take the 2 and multiply it by 2 on both sides. You can call this 2c, but really it's just a constant anyway, so you can call it c1, or you just call it bigger c, whatever you wish, okay? Still c. And then ultimately now you can actually solve, okay? So one of the methods, of course, is to solve for y, and we'll do that. So we can do this first. Don't forget when you do this to have a plus minus, but wait, you now need to determine which one of these square root graphs to actually use, okay? And if you're thinking about this, you're like, I don't know, I don't know, I don't know. Look at the actual point I gave you. Can you see how the y value is positive? So because the y value is positive, you need to use the positive root. Or you won't be able to get a chance to get a positive y value. So we'll use that. We're going to plug in the point 0, 1, and let's go ahead and solve for c. And you'll see now how this works, because root c equals to 1, or c equals to 1, and therefore the equation is y equals to the square root of negative x squared plus 1. Ta-da! Now, I know some of you are like, Mr. Lee, I'd rather you go ahead and solve for c first. Okay, if you wanted to do that, even, not even there, you could have done it right at this particular point, right here. You could have plugged in 0, 1 here and also solved for c. It works the same way. Okay? Now, finding the particular solution whose graph passes through the point 0, -3. This time, you have to think to yourself, my y value here is negative, so therefore, which one of the square roots do you need? Yeah, you need the one with the negative sign in front. So let's use this equation now to solve. I will once again plug in the point 0, -3. And voila, you see how the two negatives now cancel each other out to give you a positive. That's why that worked. And now if I were to solve for c, I get c equals to 9. So therefore, in this case, the equation is negative the square root of negative x squared plus 9. Okay? And by the way, these are graphs of semicircles. How do I know? Well, remember if I were to take this one here and if I were to square both sides, I get y squared equals negative x squared plus 1. From your pre-calculus 12 days, if I move this over, x squared plus y squared equals to 1. Hello, equation of a circle with radius 1. But of course, I have the square root and I'm only taking one portion. So hello, semicircle. Okay. So in example 5, it's kind of the same thing. This time I'd like you to go through the whole process yourself. I think you can do it yourself. Yeah, I really do. Because I've shown you the process before. This is just a different equation. And hopefully, after I've given you some time to work on it, you can then come back and check your answer with me. And hopefully we'll both be right. And we can move forward. Okay? So once again, pause the video now. Come back when you're done. Interesting how this one is just 1 over y. So that means it's just dependent upon the y value. So who cares really about the x, okay? Like for instance here, the y value is 3, right? So y prime would just be 1 over 3. So I guess I'm going to draw a pretty flat lines here for the slope fields. Okay. Here, look, y equals to 2, so y prime equals to 1 half. Half, 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 half. And 1, 1, 1, 1, 1, 1, 1. And then hopefully you see undefined, undefined, undefined. And interestingly enough, you get what? Down here, y equals -1, so y prime is -1. 45-degree line going downwards, more flat, and even flatter, right? Got that? Nice. Congratulations on finishing part 1, or part A. What happened when you graph the particular solution? If I'm going through the point -2, 1, that looks like it's here. I'm hoping to see a graph looking like this. And once again, an open dot here on the x-axis. And if you went through 2, 2, 2, 2 seems to be right here. I'm looking at the graph that looks something like this. Okay, and once again, as functions of x, so we stop here at the x-axis. We don't go any further. And if you did part C trying to solve the differential equation, once again, I replaced y prime with dy dx. I will move the y's to one side and the dx to the other. Take the antiderivative. Ooh, what's the antiderivative of 1 dx? Oh yeah, just x. And then plus c. I'm going to multiply both sides by 2, so 2x plus 2c, or just another c. And if you solve for y, dun, 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 once again, plus or minus, please, the square root of 2x plus c. Now, because I did say it's a function, well, you have to continue further and decide which one of these plus minuses I should use. Uh-huh. Uh-huh. The negative one. So once again, these two negatives divide each other out. So now it becomes positive. -4 plus c will square both sides. And I hope you can see that c equals to 5. So y equals to the negative root 2x plus 5. Did you get that? Give yourself a pat on the back if you did. Yay! And then similarly for part D, this is 2, 2. So I'm going to use the positive square root 1. 2 equals to 2 times 2 plus c. 4 plus c. Square both sides. And c equals to 0. Brilliant! Because that totally matches up what my graph looks like in the slope field. See? Goes through 0, 0. All right. So if you got those, give yourself a pat on the back. You should be proud of yourself. You understand these ideas of slope fields. But let's see if you really understand them with these two examples now. Multiple choice. Okay. So this time I gave you the slope field. But I want you to come up with the actual derivative equation or the differential equation that matches this particular slope field. You got 5 choices, A, B, C, D, E. Think about it. Pause. Don't just let me give you the answer. Think about this, okay? Try to eliminate some of them, and then hopefully you can figure out the right one. All right? I'll give you 10 seconds. Now, I hope you can eliminate some of these. Okay? I hope that you can see that it looks like the slopes depend only on y, right? Look at this. This is where y equals to 1. They all look the same. So if they're all the same, then it probably just depends upon y, like the previous example we just did here, right? All the same going across horizontally. So if it just depends on y, so goodbye A, goodbye C, and goodbye E. Okay? So your only choices now are B and D. Well, if I chose B as my correct answer, if y is negative, then my derivative or my slope should also be negative. So as an example here, my y is negative. But look, my slopes are positive. Uh-oh. Sorry, B. So yeah, B must be the answer, right? All the slopes in this slope field are positive, and the slopes only depend on y. And also, you can double check looking at these values here. When the y value is 0, is the slope 0? Nope. The slope is, yeah, kind of like 1. So if I plugged in 0 here, 0 squared plus 1, yeah, that makes kind of sense. Okay? Now, example number 7 is a little bit different because this time I said the slope field is shown, but I want you to find the specific solution, not the differential equation, but the actual solution. So then notice that your answers here are always y equals 2. So the solution is actually the original equation. Okay? Now, you can kind of continue to look at these lines and draw in a particular solution because they look like this. Okay, and really then my question to you is which one of these equations gives you a graph that looks like that? Well, I can tell you it's definitely not A because e to the x looks like this. Whoop. So sorry. And then I definitely know it's not the lawns, okay? Because negative lawn, what's that? That looks like this. Whoop. No way, right? Regular lawn looks like this. Whoop. No way. Okay? And then you're left with pretty much B and C. Okay, so how do we do e to the negative x? This negative is a reflection in the y-axis, so it looks like this. And by the way, this reflection here with the x for part C is a reflection in the x-axis. So the graph looks like this. Which one looks like the one that matches those lines not lines, the curves I drew? Yep, B it is. So there is your specific solution. Okay. Now, for those of you doing the AB, you're like, this is on review. I know. I'm glad. I'm glad it's review. Here's the extra BC stuff. Okay. You might be thinking drawing these solution curves are pretty sketchy. Get my joke? Pretty sketchy. Like not so great. How can we make it more accurate? So Euler's method is a method that gives us a more precise method of graphing an approximate solution to a differential equation. Okay? Now, Euler used a method to construct an approximate solution by just going at little baby steps, starting small and moving bit by bit by bit. Okay? So here's what Euler created. He said, okay, well, you're going to have a starting point. Okay? And in this case, the starting point is 0, comma 1. I like to make this little chart with a table because I think it organizes the work really well. So x is 0 and y is 1. Okay? Now, you need to figure out the derivative at that point. And the derivative for example number 8 is just given by the equation dy dx equals to y. So that just equals to the y value, it's 1. Now, here is what Euler did. Euler said, okay, well, we gotta find the change in y. Okay, the change in the y value. And that change is equal to the slope multiplied by the change in the x value. Okay? Think about it, slope dy dx, right? Okay, so thinking about this, the change in y over the change in x, right? If I move the delta x over, so I guess what I'm saying is this, right? Here we go, that's slope. So delta y equals to slope times delta x. All right? So in the first line here, delta y just becomes a slope of 1 times delta x. Now, what's delta x? They're saying, let's use this really small change of x of 0.1. It's given to you in the question. I'm like, okay. So I'll do that. So the change in the y value is 0.1. Now, noticing these two things, can you now complete the next line, the next iteration? You said that delta x is 0.1. So that means I have now increased x by 0.1. From the previous line, you said that the delta y value is 0.1. So that means I've increased the y value by 0.1 as well. So that's 1.1. And now this is the new coordinate that you're going to plot. So I guess I should plot at 0 point or 0 comma 1 first. Whoop. Now I'm going to have 0 0.1 comma 1.1. Whoop. And then we're going to repeat this process to get to the next value. So once again, what's dy dx? That's just 1.1. And what's delta y in this case? It'd be 1.1 times 0.1, which would be 0.11. And so now if I look at my third line, once again, delta x, the change is always constant. So now it's just going to be another 0.1 added to the previous one. That's 0.2. But notice my y value is now not 0.1, but 0.11. So 1.1 plus 0.11 is 1.21. So there is my new value. 0.2 is actually not 1.21. And then once again, we repeat the process one more time to help you figure out the y value when x is 0.3. So 1.21, 1.21 times 0.1 is 0.121. Finally, if I were to add 0.1 one more time to x, I get 0.3. And now adding the 0.121 to 1.21, that's 1.331. So my estimated value for y when x is equal to 0.3 is 1.331. Okay. And I guess the graph looks something like this. Okay. And that's how you can be more precise, because you're taking these really small delta x intervals and calculating the corresponding y values using this idea that delta y is equal to the slope multiplied by delta x. Okay. Now, if you're thinking, is that really that accurate? Well, okay, let's look at example number 9 now. Let's just solve for dy dx, okay? And then I'm going to ask you to algebraically fill in the values, and let's see how close they actually are. Okay, so once again, separate variables. There's my separating variables, antiderivative both sides. I get what? Natural log of absolute value of y equals to x plus c. To get rid of the natural log, we'll take e on both sides. So if I e both sides, I get e to the natural log of absolute value of y is e to the x plus c. And then, of course, that natural log, or an e to the natural log of y just becomes absolute value of y. I like to break up the e to the x plus c as e to the x times e to the c. And then once again, that absolute value and the e to the z just combine into a new constant. So we can just go y equals c e to the x. And remember, I gave you a starting point. So plug in the starting point to actually find out the value of c. There's my starting point. Let's plug it in. 1 equals to c e to the 0. Thank goodness c equals to 1. So we have the equation y equals e to the x. Okay? And if you were to actually plug this in now to the equation, let me pull up my calculator. Okay. E to the 0.1. Da-da-da, 1.105. And I'll do the other two as well. Okay. E to the power of 0.2. Da-da-da, 1.221. Remember, AP exam, 3 decimal places. And finally, e to the power of 0.3. Da-da-da, 1.3498 or 1.350. And look at that. That's not bad, right? 1.331, 1.30, that's pretty good as an estimate, as an approximate. Remember, approximate solution. Okay? All right. I'm going to ask you now to try number 10 yourself, okay? Because it's really similar to what we just did. So once again, use Euler's method to approximate the particular solution of this differential equation, passing through this particular point, and this time the delta x is actually 0.2, and I want you to do 3 steps. So if you don't know what that means I'm starting at 0, and I'm going to increase it by 0.2 each time. So 0.2, 0.4, 0.6, that's my third step. And I want you to find the y value at that third step. Okay? All right, so you go try that. And like I said, when you're done, come back and take a look. Press pause, please. I meant it. Press pause. Once again, dy dx is x minus y. That's the equation, right? Okay, so the starting y value is 0.5, which means now if I do x minus y, 0 minus 0.5, right? 0 minus 0.5, that's negative 0.5. Delta y now is the slope, which is negative 0.5 times delta x, which is 0.2, and that just equals to negative 0.1. Okay, so notice my new y value is now going to be less. So 0.5 minus 0.1 is 0.4. And now if I take a look at what dy dx is now, it's the x value, 0.2 minus y, so that's actually negative 0.2. And so negative 0.2 times, once again, delta x, which doesn't change, is 0.2, negative 0.04. And then once again, my y value now decreases 0.04. So what's that? 40 minus 1, 36, 0.36. And then now x minus y, 0.4 minus 0.36. Oh, look at this. It turns actually to become now a positive value. Really small though, but still positive. 0.04 times 0.2, that's 0.008. And then if you really add that to it, you get 0.368. So my final approximate value of y when x is 0.6 is 0.368. Okay. And once again, you should plot the points. So 0, 5, 0.2, 4, 0.4, 0.36. And then notice at 0.6, it just goes up a little bit. So, and then kind of goes up just a little bit. Okay. Got that? Yay. Now, to finish this off, example 11. Look, sketch a particular solution of the differential equation passing through the point 0, 0.5 using the slope field given, like what we did at the beginning of this lesson. Okay? So going through 0, 0.5, here we go. And I guess I gotta just continue through and kind of draw. So I don't know, it looks kind of like this, doesn't it? And then, yeah, it does look like it goes up a little bit. So does this graph look like the one that you kind of drew? Yeah, I think so. Yeah, maybe mine's not as low, but hey, I think it's actually pretty good. Okay, do they coincide? Yay! And because of that, now you're done lesson 7.2, and then you can now try the assignment. All right, do that please, and we'll see you back for lesson 7.3. Until then, bye-bye.